This call is now being recorded. Okay, once again, good afternoon, everyone. Last meeting, I discussed this particular subsection. We talks about ancillary statistics. So we have in definition 6.2.16 the definition of an ancillary statistic, which is a statistic actually whose distribution does not depend on the parameter theta. And we have several examples illustrating this definition. The first one, we have the uniform ancillary statistic. And then we were able to show that the range, which is actually the difference of the maximum order stat minus the minimum order stat, is an ancillary statistic because we have shown that the PDF of our range does not depend on our parameter theta. Okay, the next one, applying still the definition, we have the location family ancillary statistic. So we have a random sample, x sub 1 up to x sub n, in which the observations come from the location parameter family. That means the CDF is of this form, big F, x minus theta. And then our theta ranges from negative infinity to positive infinity. And in this example, we have shown that the range is still an ancillary statistic. And we have used this theorem 3.5.6, which is actually a theorem for the location scale parameter family. In other words, the transformation from z to x. Okay, using this theorem 3.5.6. And then on the next example that we have a random sample. Okay. Okay, sorry. A random sample coming from, or whose observations are coming from a scale parameter families. No? Family. So we have this CDF, a big F, x over sigma, where sigma is positive. Then any statistic, so in other words, any statistic which is a function of our sample only through the n minus 1 values. So we have here the x sub 1 over x sub n up to x sub n minus 1 over x sub n. So we have a function, a function that depends on this sample only through the n minus 1 values. Having this form is also a ancillary statistic. Say, for example, we have here a statistic. This is a statistic. This is a function of the sample only through the n minus 1 values of x sub 1 over x sub n up to x sub n minus 1 over x sub n. Okay, so we can write this as t of x. Pwedeng ganun. We have that. And this, we have shown that the function or the statistic t of bold x is an ancillary statistic. Okay, using again the transformation that we have in theorem. We have theorem 3.5.6. So let me continue now on this subsection in which we have a sufficient ancillary and complete statistics. So a minimal sufficient statistic is a statistic that has achieved the maximal amount of data reduction possible while still retaining all the information about the parameter theta. So intuitively, a minimal sufficient statistic eliminates all the extraneous information in the sample that does not contain the information about the parameter theta. So only retaining the piece with information about the parameter theta. So it might be suspected that a minimal sufficient statistic is unrelated to, or mathematically speaking, functionally independent of an ancillary statistic. But we're going to show this also in what situation that we can say that an ancillary statistic is independent of a minimal sufficient statistic. So however, this is not necessarily the case. So in this section, we investigate this relationship in some detail. So we have here a remark. So we have already discussed a situation in which an ancillary statistic is not independent of the minimal sufficient statistic. We have that in example 6.2.15, in which we have a random sample coming from a uniform theta plus 1 distribution. Okay. And then at the end of section 6.2.2, we noted that this statistic, okay, this statistic, which is actually a statistic comprising of the statistics, the range and the mid-range, is a minimal sufficient statistic. As in example 6.2.7, no? Is a minimal sufficient statistic. And then in example 6.2.17, we have shown, okay, we have shown that the range is an ancillary statistic. Take note, in itong sa end of 6.2.2, before having this remark in 6.2.2, we have actually shown that the statistic, itong statistic na to, for this given example, we have the minimum order stat and then the maximum order stat. This is a minimal, okay? It's a minimal sufficient statistic. And I have shown to you before that a function of this minimal sufficient statistic, and this function is a one-to-one function, and that would imply a one-to-one function. That is why we have this sufficient statistic now is also a minimal sufficient statistic, because this is a function of our minimal sufficient stat here above. Napakita ko ito, no, before. And then we have shown that the range in the location parameter family as well as in the scale parameter family, that the range is an ancillary statistic. Take note that in this statistic, itong statistic na to, the range is a component, no? Is a component of this minimal sufficient statistic. So, ano ini-imply dito? Thus, in this case, the ancillary statistic is an important component of a minimal sufficient statistic. Certainly, the ancillary statistic and the minimal sufficient statistic are not independent. So we have this case that we have shown that the ancillary statistic and the minimal sufficient statistic are not independent. Okay, to emphasize the point that an ancillary statistic can sometimes give important information for inferences about our parameter theta, we give another example. So let x sub 1, x sub 2 be IID observations from the discrete distribution that satisfies the probability that x equals theta, given the parameter theta, is equal to the probability that x is equal to theta plus 1 given the parameter theta, and it is equal to the probability that x is equal to theta plus 2 given the parameter theta, and this is equal to 1/3. This actually implies a probability distribution, no? Because the sum of these probabilities sum to 1 and the probabilities is less than 1. So where theta is the unknown parameter, theta is any integer. Say we let the minimum order stat is less than or equal to x sub 2, or the second order stat, be the order statistics for the sample. So it can be shown with an argument similar to that in example 6.2.15 that the range and the mid-range is a minimal sufficient statistic. While in the book, hindi naman naipakita yung solution to this, that indeed this statistic containing the components R, the range and the mid-range, is a minimal sufficient statistic. Let us try to show this. Okay, we have the okay, so we have the joint density given our parameter theta. This is equal to 1/3. If our x sub I is greater than theta but less than or equal to theta plus 2. I here from 1 to 2. And then we have the assumption that our theta is an integer, is any integer. And then it is equal to 0 otherwise. Parang example na rin ito sa previous natin na discussion. So this is equal to 1/3. Say the maximum of the x sub I is less than, minus 2 is less than or equal to theta, but theta is less than or equal to the minimum of the x sub I. The reason for this, since yung minimum of the x sub I is less than or equal to, or rather, it's greater than or equal to theta. And the maximum of all this realized value x sub I is less than or equal to theta plus 2. Okay, that's why we have here for our condition. And this is 0 otherwise. Okay, so if we want to show that the statistic containing the components range and mid-range is a minimal sufficient statistic, we're going to show first that the order stat, the first order stat and the second order stat is a minimal sufficient statistic. So we have this ratio, the ratio of PDFs. Okay, this ratio of PDFs given these two sample points x and y. This is independent. Okay, it is independent of the parameter theta. We have this assumption, no? If and only if we have here the minimum of x sub I would be equal to the minimum of the y sub I for all I, and at the same time the maximum is equal to the maximum of the y sub I for all I. Okay, independent. It's independent of our parameter. Makikita mo naman yan dyan using that ratio. So if we're going to let this x sub 1, this is a random variable which is equal to the minimum of all these random variables x sub I, and then x sub 2. Dalawa lang naman yung I natin. So it would be the maximum all the x sub I. And then if we're going to let R here, which is a function, huh? Ulit. Mali mo na. So letting that one, so, sorry, x sub I, and so by theorem 6.2.13. Okay, since the ratio of the PDFs is independent of theta, then by theorem 6.2.13, this statistic T of the sample, random sample, having this component X sub or the minimum order stat and the maximum order stat is a minimal. Okay? It's a minimal sufficient statistic. Pero ang gusto natin malaman na this one, this statistic containing the components range and the mid-range is a minimal sufficient statistic. Eh yung napakita pa lang natin na ang statistic na T of X having these components, the minimum order stat and the maximum order stat is the minimal sufficient stat. So how are we going to show that this statistic having the components range and mid-range is a minimal sufficient statistic? So we can have this function now. We let R, okay? We let R of our minimal sufficient stat be equal to this, yung range, x sub 2, x sub quantity 1. And then we can have M of our minimal sufficient stat be equal to the mid-range. M yung ginamit natin. So we have x sub quantity 1 plus x sub quantity 2 divided by 2. It is easy to verify. It is easy to verify that both function R and M are one-to-one functions. Based on our remark, that would imply that the statistic containing the components range and mid-range is a minimal sufficient statistic. Pwede nyo sabihin natin, thus, this statistic containing this component R and M is also a minimal sufficient statistic. Okay? Kung gusto niyo malaman, say for example, gusto natin malaman ito. Say R. R here is a one-to-one function. Yeah. Check. If you want to show that R is a one-to-one function. Say for example, no? It's easy to verify man lang daw. Hindi lang natin i-show sa M. Show R is a one-to-one function. Ano nga yung sa one-to-one function? You're going to assume that R to the T of X for any two sample points is equal to R to the T of Y. It's according to showing that it's a one-to-one function. No? And then we're going to show that T of X is equal to T of Y. So ano yung R of T of X? So this is equal to X sub 2 minus X sub 1 is equal to Y sub 2 minus Y sub 1. And this would imply that we have X sub quantity 1 is equal to Y sub quantity 1, X sub quantity 2, the realized value, Y, a small letter yan siya, quantity 2. So this would further imply that the ordered pair, X, ordered pair tayo, would be equal to the ordered pair Okay? Showing that t of x is equal to t of y. Therefore, r is 1 to 1. Okay? Nakaka lang yan, no? You can show also that m is 1 to 1. So, we have that. Since we've expressed, uh, now we have expressed the range as a function of the minimum and the maximum order stat, and we have shown that this function is 1 to 1, as well as the mid-range. This function is also the function of the order stat, which is equal to the mid-range, is also the function is 1 to 1. Then we have shown that this component, okay, ito is also a minimal sufficient statistic. Okay, napakita natin tong part na to is a minimal sufficient statistic. Yung R sub m, R and M is a minimal sufficient statistic. Okay, next. Sabi pa dito, uy, putol pala to. Send lang. Oh. It says here that X sub 1 minimal sufficient statistic. Transfer na lang tayo sa ibang notes muna ha. Kasi ito, continuation. Continuation yan. Okay? So we have shown that R sub M is a R and M is a minimal sufficient statistic. Yun yung solution natin. Then, minimal siya, no? Minimal itong R and M component with components R and M. Then we're going to show that R is an ancillary statistic. And then we're going to show how R might give information about theta. That is why in this example, the ancillary statistic is not independent of the minimal sufficient statistic. So, paano natin malalaman na ang R is a ancillary statistic? Reason yan. Ito yung nakasulat. To see how R might give information about theta, even though it is ancillary, consider the sample point. Wala pa naman siyang, sulat ko na lang dito, no? Okay. We're showing R is an ancillary statistic. Since the random sample, our random sample come from a location, come from a location parameter, no? Based on our given problem, come from a location parameter family. Then we have shown it in our last meeting that our range R is an ancillary statistic. Okay, so R is an ancillary statistic. So show how R might give information about theta, about our unknown parameter theta. So to see how R might give information about theta, even though it is ancillary, consider a sample point Rm. Okay, this is our sample point Rm, and then where m is an integer. Say first we consider only m. Given yung m, we consider only m. For this sample point to have a positive probability, theta must be one of the three values. Either theta is equal to m, or theta is equal to m minus 1, or theta is equal to m minus 2. So how are we going to show that one? Dito ko na isulat, no? From m, which is our mid-range, we have here x quantity 1 plus x quantity 2 divided by 2. So first case, when the realized value of the first order stat is equal to the realized value of the second order stat, say this value is equal to theta. Because we know that our theta ranges, no? Uh, rather the value uh, of our x, no? The value of our x uh, ranges from theta to theta plus 2. Kasi ito lang yung mga possible values ng theta natin, ng x natin. So theta, theta plus 1, theta plus 2. So the values of x ranges from theta to theta plus 2. So kunwari yung mga realized values niya, the first order stat and the second order stat is equal to theta. So this would imply that our m would be equal to what? Theta plus theta over 2. So this would further imply that theta is equal to m. And this is an integer. Next, we're going to choose all the possible values of this. Sorry. Say x sub 1 here, the realized value would be theta. And then the x sub quantity 2, we have here theta plus 1. So this would imply that m, we have theta plus 1 divided by 2. And this implies that theta is equal to 2m minus 1 over 2. And in this case, this is not an integer. So next, yung realized value ng first order stat, theta. Yung maximum order stat is theta plus 2. This would imply that m is equal to theta plus 2 divided by 2. So we have here theta is equal to m minus 1. And this is also an integer. Okay, next. Theta 1 would be equal, theta sub 1 would, x sub 1 would be theta plus 1. And then yung x sub 2, quantity 2 is theta plus 1 then. So this would imply that m here, we have theta plus 1 plus theta plus 1 divided by 2. So this implies that theta is equal to m minus 1. This is still an integer. Another case, yung theta plus 1, yung x quantity 2 is theta plus 2. This would imply that m is equal to theta plus 1 plus theta plus 2 divided by 2. Imply that theta is equal to 2m minus 3 divided by 2, and this is not an integer. And then lastly, yung value ng first order stat would be theta plus 2, and then the maximal over stat is also theta plus 2. So this implies that m is equal to theta plus 2 plus theta plus 2 divided by 2. This implies that theta is equal to, in this case, we have theta 2, so we have m minus 2. And this is an integer. So ano yung mga possible values natin ng theta? Theta should be a positive, no? Should be an integer. Yung theta natin. Unknown is an integer. So ito lang yun. This, pareho lang naman yan sila. And then this. So given an m, the value of our mid-range, the possible values of our theta. So ito yung mga possible estimates or estimate of our theta. So theta could be m, theta could be n minus 1, or theta could be m minus 2. Okay, ito yun. Theta could either be m minus 1, or theta could be m minus 2 with only the information that our big M is equal to small m. So we have three possible values for our theta. But now suppose that we have an additional information that our R, itong R natin ngayon, that our R, the range, the value of our range is equal to 2. So then it must be the case that kung ang R is equal to 2, yung range niya is equal to 2, so yung value ng first order stat, ito, the value of the first order stat should be m minus 1, and the value of the second order stat should be m plus 1. Because if we're going to add these two, kaya ang range, the maximum order stat, or x sub 2 minus x sub 1, so we have an answer which is equal to 2. No? We have an answer is equal to 2. Or in other words, we can have this. R equals 2, no? Implies that the x sub 1 would be equal to m minus 1, and the value of the maximum order stat is equal to m plus 2. If and only if, pwede din naman sabihin natin, if and only if, and the value of our first order stat is equal to theta, kasi yung mga possible values of theta natin, di ba? Possible values of the x natin. Kasi yung x, yun ang mga possible values ng x natin. Ito lang, it ranges from, yung mga x sub I natin dito, it ranges from theta to theta plus 2. Okay, we have here theta, theta plus 1, theta plus 2. Theta, theta plus 1, up to theta plus 2. So in this case, that our the order or the value of our first order stat is theta, if and only if the value of the maximum order stat is equal to theta plus, okay, we have here theta plus 2. So when the value of this order stat is equal to that, ito yung na case. Yan. In a case. So that means, that implies that the only possible value of our theta is equal to m minus 1. Yan. Kita mo natin yan dito. No, ito, yung itong part na to. Theta is equal to m minus 1. So, given the value of our range, it says here, no, of course, thus the knowledge of the value of the ancillary statistic R has increased our knowledge about theta. Kasi kung mid-range lang yung given natin kanina, yung m lang, we have three possible values of our theta. Theta is unknown. It's an unknown parameter, and we're going to estimate this unknown parameter. So if the mid-range is given as m, so we have three possible values of theta. But if we have an additional information that R is equal to 2, then it would imply that the only possible value of theta is equal to m minus 1. So increased, no? Of course, the knowledge of R alone will give us no information about theta because it is an ancillary statistic. The idea that an ancillary statistic gives information about the precision of an estimate of theta. Okay, so ito yung example natin that an ancillary statistic, not independent with the minimal sufficient statistic, and this ancillary statistic would sometimes give information for inferences on our parameter theta. Okay? So for many important situations, however, our intuition that the minimal sufficient statistic is independent of any ancillary statistic is correct. Totoo naman yan. But when will this situation happen? Na, kailan mangyayari na ang minimal sufficient stat independent siya sa ancillary statistic? So, this will happen when we have situation in which this occurs relies on the next definition. So, kailan mangyayari na independent yung ancillary sa minimal sufficient statistic? So, consider this definition. Let f of t given the parameter theta be a family of PDFs or PMFs for a statistic P of the random sample. The family of probability distributions is complete if the expectation of G of t given the parameter is equal to 0 for all theta, implies that the probability that G of t is equal to 0 given theta is equal to 1 for all theta. So that means that we have a sure event here because the probability is equal to 1 for all theta. So equivalently, this statistic T of the random sample X is called a sufficient statistic. Take note that in our definition, this statistic is a complete statistic if the family of probability distribution is complete. No? Itong sabi dito, itong statistic na to, complete statistic siya if the family of probability distribution is complete. So kailan mangyayari na ang family of probability distribution is complete? If the expectation of G of t given our parameter theta is equal to 0 for all theta, and then if it would imply that the probability that G of t is equal to 0 for all given theta is equal to 1 for all theta, then the family of probability distribution is complete. Pwede natin may sulat yan. For a family of probability distribution is complete if the expectation of G of t given our parameter theta is equal to 0 for all theta. This would imply that the function G of t, this function of G of t will be equal to 0 with probability 1 for all theta. Okay, so based on our definition, the completeness is a property of a family of probability distributions, not of a particular distribution. Say, for example, if X has a normal distribution with mean 0 and variance 1, in other words, X is completely specified. We have no parameter here for our random variable X. Okay? Then if we're going to define our function G of X is equal to X, for our function G is simply the identity function. So our assumption that the expectation of G of t or the expectation of G of X, and by identity, G of X is equal to X, and the mean of X, this random variable X is equal to 0. Can we check that the probability that G of X is equal to 0 is equal to 1? So given this identity, this function, so it satisfies this probability, the probability that G of X equals 0, kasi gusto natin i-check if it is equal to 1. And then since G of X is equal to X, so we have the probability that X equals 0, okay? And the probability that X equals 0 is equal to 0 because we know that X is a continuous x is a continuous random variable, and the probability that a continuous random variable to a specific value will be equal to 0, and that is not equal to 1. 0 and not 1. So in this case, this x, random, no, sabihin natin yan, is not a complete statistic. However, if we're going to consider x having this distribution n theta 1, meaning the mean is equal to theta, and then the variance is equal to 1, where theta ranges from negative infinity to positive infinity, we shall see that no function of x except 1, that is the zero function with probability 1 for all theta, satisfies that the expectation of g of x given the parameter theta is equal to 0 for all theta. So meaning to say, itong 0 dito, this actually refers to the g function. Ibig sabihin yan, that is the zero function of our sample, of our random variable, will be equal to 0. You have that, no? That would be equal to 0. Or, ibig sabihin pala niyan, no? We have this probability 1, zero function, the probability of this, the zero function of x, okay, zero function man siya, of any random variable x is equal to 0. Obviously, this is a sure event. So we have probability 1. Kaya ito, that's for all theta. And this satisfies our assumption that the mean, the expected value of our g of x, etong g of x natin, itong g natin dito, it refers actually to the 0. Yung g of x yan, ibig sabihin yan, that's the 0 of x. 0 nito is 0 function. So, no function of x except one that is 0. Yan ibig sabihin yan. No function of x except one that is 0 function. So a function x with probability 1 for all theta. So yeah. Since it satisfies our definition, thus the family of n of theta 1 distribution is a complete, family. Okay, so let's have an example showing or finding a complete statistic based on our definition. So consider example 6.2.22, binomial complete sufficient statistic. Suppose that T has a binomial, okay, it has a binomial NP distribution, and we restrict our P to be greater than 0, but less than 1. And then we let G be a function such that, based on our definition, i-assume natin yan, the expectation of the G of T given our parameter P. Itong case na to, no? Itong part na to. That's for all your parameter. Kaya ito na yan. We assume that for all, no? That's for all P. Greater than 0 but less than 1. We assume it to be equal to 0. And we're going to show that the probability that G of T G of T equals 0 for all the parameter P would be equal to 1 for all parameter P. So by our assumption, assumption ito, first equality by assumption. Yung second equality, by applying the definition of expectation. So these the finite summation of g of t times the probability mass function of t. Ano naman yung t pala? T has a binomial. Kung meron siyang binomial NP distribution, so yung kanyang PDF nito, sabihin natin f big T of small t, we have here combination of n taken t at a time. Then we have the probability of success raised to t, 1 minus p raised to n minus t. Okay? The value of t from 0, 1 up to n. Kaya ito. Ito yung ating is by definition of expectation. And then second, this equality here, we're going to put the factors that does not depend on the index of our summation before our summation. So ito, paiwan natin, napalabas natin ito. So ito yung maiwan sa labas. Okay, so for all p greater than 0 but less than 1. Since this is equal to 0, ito equal to 0, but the factor 1 minus p raised to n is not 0, then we are forced to imply that this remaining factor would be equal to 0. Yeah, would be equal to 0. And then letting r be equal to p 1 minus p. So we have this. That's for all r greater than 0 but less than infinity. Okay, so the last expression, itong last expression na to, here, is a polynomial of degree n in R. Because if we're going to take the sum, the last possible value of t there is n. So it's a polynomial of degree n in R, and then the coefficients of, or the coefficient of R of t is, we have this expression, g of t times the combination of n taken t at a time. Okay? So kung yung polynomial natin is to be equal to 0 for all r, and then for each coefficient must be equal to 0, kasi equal to 0 dapat siya. Parang equating terms ito. Sabihin natin equating terms. 0 dito. Okay? 0, and then this one. Equating terms. So the first coefficient is equal to 0. The second coefficient is equal to 0. So imply, for all to be 0, the coefficient must be 0. So none of this combination of n taken t at a time is 0. So hindi pwede ito maging 0. Kasi yan yung coefficient niya. So that would imply that g of t will be equal to 0. Excuse me for a while. Unsa na? Sorry for the interruption. So that would imply that g of t is equal to 0 for t, for these possible values of t, 0, 1 up to n. Okay, since t takes the value 0 up to n with probability 1. So obviously, with probability 1, it takes the value, this random variable t takes the value 0, 1 up to n with probability 1. Then we have shown that the probability of g of t is equal to 0, given the parameter p is equal to 1 for all p. So the desired conclusion, so implying that our family of distributions is complete, and it would also imply that our statistic t is a complete statistic. Any questions or clarifications? napakita natin, no? Based on our definition that the family of distributions, the family of the binomial distributions, NP is a complete, no, is complete. Therefore, T is a complete statistic. Guys, any questions or clarifications? None so far? Are you there? Okay lang?
Yes, sir.
Okay. Lima na day mo? Okay, let me continue. Example 6.2.23. So in this case, we have a uniform, complete, sufficient statistic. Let x sub 1 up to x sub n be IID uniform 0 to theta. Observations where theta is greater than 0 but finite, less than infinity. So using an argument similar to that in example 6.2.8, we can see that the function of our random sample or sample T of bold X, which is the maximum order stat, is a sufficient statistic. And by theorem 5.4.4, the probability of this statistic T of X is this. Meron, yan na yung nakasulat yun sa book. I'm going to insert the details solution to that. So yung PDF. Ano yung PDF ng X natin? X having a uniform distribution. So we have B, pwedeng ganun. Pwede natin ilagay yung 0. Pwede din wala. Pwedeng ganun, no? But we have the parameter theta. And this is equal to 1 over theta minus 0. Okay? And then you have the indicator function of X on this closed interval. And this would also imply that our CDF for this, we have X minus theta, or rather X minus 0 divided by theta minus 0. You have your indicator function X 0. Or simply we have X over theta, then you have the indicator function. Ayan. Yung joint. Ano yung joint PDF ng ating random sample? Ayan, bold na yan. So we have here. Pwede wala itong 0 ha. Pwede yung parameter lang niya. So obviously, we have 1 over theta. So joint yan siya. We have here F X 0 theta raised to n. Okay, that's raised to n. Or we can have 1 over theta. So theta to the negative n, and then we have here the product of the indicator function x sub I 0 to theta. I from 1 up to n. Or we can simply write this as theta to the negative n. Pwede ganito yung pagkasulat natin. Yung value na x sub I greater than 0 or less than theta plus 4 I 1 up to n. Or pwede din natin masulat ito na theta to the negative n Then we have this, yung x sub I natin is an element from 0 to positive infinity. Okay, positive infinity. For I, 1 up to n, and additional, no? And the maximum. The maximum of the x sub I for all I is less than or equal to theta. O, pwede yan. So, ibig sabihin, itong part na to, pwede natin may sulat na ganito. Ha? So, if you're going to define, so if we're going to define now our T of our sample, observed sample, T of x would be equal to the maximum of the x sub I. Let's have this to be equal to T. So it would implies that ang factor natin na h of x, factor of the sample, observed sample, would be equal to 1. Okay? It would be equal to 1. That's for all x sub I, element 0 to positive infinity. That's for I, 1 up to n. It's a factor of x, it's a function of x natin dito. And, okay? And, yung function, okay? G. Sabihin natin na G of t given our parameter would be equal to what? In this case, would be equal to theta to the negative n, and then we have the maximum. Where t here, maximum yan t. T is the maximum of all xi, less than or equal to infinity. Okay? So thus, yung ating joint PDF, can be factored as h of x. Yan, ma-factor natin ang h of x. And then, function of our sample, g of t. So, ano implication nito? So, our t of this random sample, which is equal to the maximum of all the random variables, is a sufficient, it's a sufficient statistic by factorization theorem. Yan, so napakita natin ito na it's a sufficient statistic. Yan yung solution. Parang review lang yun na part, no? Next, and by theorem 5.5.4. You have this in stat 331. Say maximum order stat nun siya. So pag maximum order stat siya, sabihin natin, we have this note, no? The maximum order stat, recall this one, x sub n. Say we have here x, given our parameter. Kung meron tayong parameter, ano nga itong formula nito? That's in theorem 5.4.4. We have here n factorial over n minus 1 factorial, and then n minus n factorial. We have the PDF of x, evaluated at x, the CDF of our random variable x, x tayo, no? CDF raised to n minus 1, and then we have here 1 minus the CDF, raised to n minus n. Okay. So in this case, n minus n, so itong part nito magiging 0 lang ito. Yung part na yan. So, palitan natin yung x by t. Palitan natin yung small x by t. T na lang. Given the parameter. So, yung formula. This would be equal to 0. So, itong part na to, n factorial divided by that, we have this n. N lang yan, yung result niya. Using above, yung PDF niya, above. Yung PDF above is 1 over theta. What about the CDF? Nandun yung sa itaas, no? Ito, itong part na to. Ayan. The CDF natin, we have T. So we have T over theta raised to n minus 1. Now this is for T greater than 0 but less than infinity. Okay, so we have this result now. This is now the PDF. Ito lang, may order stat lang tayo dito, maximum order stats. That our T of x, x of n. And then 0 otherwise. Okay, so yan yung ating PDF. So by theorem 5.4, we have that. Suppose we have this g of t now. Ito yung assumption natin sa definition. G of t is a function satisfying that the expectation of g of t given the parameter is equal to 0 for all parameter theta. We have assumed that to be equal to 0. So it's a constant as a function of theta. So if we're going to take the derivative of this expectation with respect to theta, so it would be 0. Kasi constant siya, so we have these results. It would be 0. We take the derivative with respect to theta. Okay, 0. And then this next equality here, applying the definition of expectation, having we have a continuous random variable. So we have this the integral of g of t, and this is now the probability density function. Okay, that's a probability right here. It's the probability density function of our statistic t, dt from 0 to infinity. Okay. So in other words, we can express this as d with respect to theta. We can write the factor before the integral sign that does not depend on t. So we can have theta to the negative n. And then yung maiiwan sa ating integrand should be a function. This function, g of t, n, t, n minus 1 dt. So the derivative of the product with respect to theta, say, parang ito, you take the derivative. Say, derivative of the product fg. So it would be f times g prime plus g times f prime. So parang ito yung f. Ito yung f natin. Oh no. So parang ito yung f. Ito yung f. Ito yung g, function g. Ito yung function g. So derivative of the product would be equal to f times the derivative of g plus g times the derivative of f. Okay, ito. You copy f, you take the derivative of g. Ito ngayon, plus the derivative of f, you copy g. So applying the product rule for differentiation. And we have this result, saying the first term in the next of the last line is a result of application of the fundamental theorem of calculus. Kanitong part na to, we take the derivative with respect to theta, and then we have the integral of this from 0 to theta, obviously, the derivative or the differentiation integration. Then we have these results, okay, for the first term. What about the second term? Why is it is equal to 0? If you're going to take the derivative of theta to the negative n with respect to theta, okay, itong answer na to, part na to, that would be negative n theta to the negative n minus 1. And then still you're going to copy your integral n g of t to the n minus 1 dt. Ito lang yung part na to, ha? So this would be equal to negative n, okay? This would be equal to n theta to the negative 1, 0 to the theta, n g of t to the n minus 1. So meron tayong theta to the n. Okay? Theta to the n, negative n rather, dt. And this is actually equal to, itong part na to, equal ito sa the expectation of g of t given our parameter theta. And we have assumed this to be equal to 0. We assume this to be equal to 0. Yan. Ito yung part na yan. Assumption to be equal to 0. So the second term will be equal to 0. So ang naiiwan na lang itong part na to, that 0 is equal to theta to the negative 1 n times g of theta. Okay, simplify lang naman ito, itong part na to. Sinimplify lang natin. Okay, since it is equal to 0, and then we know that theta to the negative 1 times m will not be equal to 0. So we're going to imply that g of theta is equal to 0, and this is true for every theta, no? For every theta greater than 0. So itong part na to, g of theta is equal to 0. This is true. No, this is true. Theta is equal to 0. That is for all. Okay, this is true with probability 1 for every theta greater than 0. Or pwede natin siyang sabihin, the probability that g of theta is equal to 0 g of theta for all theta now. Okay, so we have satisfied the condition in our definition. So in other words, the family of distribution is complete. Therefore, we conclude that our T is a complete statistic. Okay, so we have verified, we have illustrated our definition by these two examples. Okay, complete na. Okay, complete. We have a complete statistic. Now we use completeness to state a condition under which a minimal sufficient statistic is independent of every ancillary statistic. In our previous examples, we have seen that the minimal sufficient statistic as well as the ancillary statistic are not independent. Actually, the ancillary statistic is a component, a component of our minimal sufficient statistic. Pero ito ngayon, pag yung statistic natin na T of X is complete and minimal sufficient statistic pa siya, then T of X is independent of every ancillary statistic. That's actually our Basu's theorem, theorem 6.2.24. Okay, so Basu's theorem is useful in that it allows us to deduce the independence of two statistics without ever finding the joint distribution of the two statistics. So to use the Basu's theorem, we need to show that the statistic is complete. Eh, itong kailangan natin. Hindi lang yung minimal, but we're going to show it's complete, which is sometimes rather difficult analysis problem. Mahirap yung pagpakita na yung statistic complete because to show that the statistics complete, you're going to show first that the family of probability distribution is complete, satisfying the conditions that we have in our definition. But ang sabi lang dito, fortunately, most problems we are concerned with are covered by the following theorem. So we just limit ourselves in which we have a random sample coming from an exponential family of distributions. So complete statistics in an exponential family. So the PDF or the PMF can be expressed as this: h of x, c of the parameter theta, the exponential of the finite summation of the product of the function of the parameter and a function of our sample j from 1 up to k, where our parameter theta here is a vector. There's a vector of parameters, theta 1, theta 2, up to theta sub k. So in other words, we have k number of parameters in our vector. Then the statistic. This is our statistic. In this case, our statistic is a vector of statistics. So ito yung mga components ng ating vector of statistics. We have the finite summation of the t sub 1, x sub I from 1 up to n. The summation of t sub 2, x sub I from 1 up to n, up to t sub k, I from 1 up to n, is complete. So this statistic is complete as long as the parameter space. Take note, magkaiba ito. This is bold theta na malaki. Bold big theta. While this one, this is bold small theta. So this bold small theta is just an element of this parameter space, bold big theta. And this parameter space contains an open set in R to the K. Sometimes it would be difficult for us to show that our parameter space contains an open set in R to the K. Take note, we have here an R to the K. Ang ibig sabihin nitong R to the K, we have here a K vectors of real numbers. Now, K vectors of real numbers. Since, take note, since our statistic is a vector of statistics having K components. Meron siyang K components. So dapat yung parameter space natin contains an open set in the K, the K vector of real numbers here. So K vector of real numbers. And at the same time, the vector of our parameter, bold theta, has also K components. Pag ito mapakita mo na yung statistics mo merong K components, tapos yung vector of your parameter mo has also K components, you can be sure that your statistic is complete. Yung book, hindi wala siya nagbigay ng example. No? Diretso na kaagad siya sa problem in which we're going to use the Basu's theorem as well as this theorem for a particular problem. Theorem 6.2.25 and the Basu's theorem. Pero let's have an illustration to this theorem. Alam naman natin ito. And so I've given this before na kung meron tayong random sample IID, random sample IID yan siya, from a normal distribution with mean mu and variance sigma square, both mu and sigma square are unknowns. Okay? So looking at the PDF, ano yung PDF natin? For a particular 1 over the square root of 2 pi, then we have here sigma, okay? We have the exponential of negative x minus mu quantity square over 2 sigma square. And then our x here from negative infinity to positive infinity. Pwede pa naman natin sulat yan dyan dito. Positive, all real numbers pala to. Pero pwede na itong wala nitong yung condition for the parameter. Pwede yung ganun. So, we have now 1 over the square root of 2 pi sigma exponential function. Then we have the negative x square minus 2x mu plus mu square divided by 2 sigma square. Okay. Okay, so we can write this as square root of 2 pi sigma. We have the exponential function of the negative mu square over 2 sigma square. And then we have also the exponential function. Ano yung exponential function natin? We have negative 1 over 2 sigma square. We have x square plus 2x mu over 2 sigma square. So mu over sigma square. Then x. Okay. Yan. Actually, ang implication yan ngayon, yung t of x natin, t, the statistic, which is a vector of statistics. So in this case, we have here the summation of x sub I square, I from 1 up to n. And then we have here the summation of xi, I from 1 up to n. So we have a vector of two statistics. Actually, yung ating parameters, yung parameter theta natin is a vector of two parameters, mu and sigma square. Pareho sila. Actually. So, okay. So, ang implication nga nito, this is a sufficient. It's a sufficient statistic. Based on our previous example, 6.2.10, no? It's a sufficient stat. Yung sa primera pa natin yan, that's by theorem 6.2.10. Ano natin malaman ito na complete siya? Complete. Because our parameter, theta, it's a parameter, it's a vector of parameters having two components, mu and sigma square. Okay, mu and sigma square. This is in the parameter space. Okay, this is in the parameter space. This is bold. Ganun naman yun. But in this case, we have now R, set of real number, the set of the positive real number. So itong mu natin, set of real number. Yan. Yung ating variance. Positive. Okay, ito. So this is actually an ordered pair. Meron tayong cross product dito. Diba? We have a cross product of two sets. The set of real number and the set of positive real number. So in this case, no, we have implied now. Okay, so yung t of x natin dito is a complete statistic. Based on theorem 6.10, 6.2.10, sufficient statistic siya. Based on this theorem 6.2.25, complete siya. It's a complete statistic. So we can say we have a complete, sufficient statistic. Okay?
Almost.
Understood, guys? Kunwari, ito. Let's have a note here. Nandun ito sa book, no? Note. Na kunyari, meron tayong x sub 1 up to x sub n. And this time, random sample din ito from a normal distribution with mean mu and variance mu square. What is our parameter here? Guys, ano yung parameter natin dito? Is it a vector or simply mu? In this case here, we take theta here, we have mu. But if we're going to simplify, our PDF, same as above, parang ganito, or the PML, or the PDF. So the dimension, take note, yung dimension ng ating statistic, T of X, dalawa. Ito pa rin yung makukuha natin. But the parameter, yung dimension ng parameter natin dito, dapat hindi siya nagkano yung mu. Wala siyang mu. Pero ang mu na, yung parameter natin is simply theta equal to mu. It's not a vector of parameters. So hindi magkapareho. Unlike dito sa first example natin. Yung vector of parameters having two dimension, the vector of statistics, or
This one the hardest.
statistics natin is a vector of statistics having two, containing two statistics or two components. So in this case, we do not have a complete distribution here.
And I die 100 times.
Okay, guys?
I die 100 times.
I hope naintindihan nyo yan.
I need to watch you.
What time? 2:57? Actually, ito na yung last na part. Okay, using Basu's theorem, we give some examples using the Basu's theorem, the Basu's theorem, theorem 6.2.25, and many of the earlier results in this chapter. So using Basu's theorem, let x sub 1 up to x sub n be ID exponential observations with parameter theta. So pag x having an exponential, theta. So yung PDF niya, we have here 1 over theta e to the negative x over theta. Okay, so then we know that theta here is positive, greater than 0. We know that the mean of this would be equal to theta, and the variance of this would be equal to theta square. And you know, so let IID consider. Take note, we're going to compute the expected value of g of x. So this g of x could be expressed as 1 over x sub 1 dot 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 plus x sub n over x sub n. Or this would be expressed as 1 over x sub 1 over x sub n dot 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 plus x sub n minus 1 over x sub n plus 1. Ayan. Diba yung sabi natin kanina, yung example natin before. First, note that the exponential distribution form a scale parameter family. Okay, based on this, it formed a scale parameter family. And we have this in our example. Ang g of x, which is a function, no? G of x here, which is a function of the sample on the n minus 1 on the n minus 1 values. Ito on the n minus 1 values is an ancillary statistic. We have that in our previous example. Bago ako nagsimula kanina, ni-review ko yan. in a location and a scale parameter. So this g of x is an ancillary statistic based on that, no? Kasi general yung form natin yung sa example na, basta mayroon tayong scale family, scale parameter family. And take note that the exponential distribution also form an exponential family. So based on theorem 6.2.25, it has a exponential family. Kung titingnan mo ito ngayon, titingnan mo yan. Diba, 1 over theta. So ang h of x natin dito na case, h of x is 1. A parameter of theta, function of theta is 1 over theta, and then e to the negative. So ang x dyan, function of theta in the exponential, 1 over theta, and then a function of x is x. Or simply, t of x is equal to x. And so by theorem 6.2.25, this one, okay, this one is a complete statistic. And based on theorem 6.2.10, this is also a sufficient statistic. Meron tayong ancillary statistic. Itong t of x, complete sufficient statistic. Pero according to Basu's theorem, it should be complete minimal pag yun. Dili lang sufficient, complete sufficient, complete minimal. So kulangan ta magpakita na kani siya minimal. As noted below, we need not verify that t of x is... Itong sabi niya, as noted below, notation niya kanina, below, but we need not verify t of x is minimal. Although we could easily be verified using 6.2.13. Ano itong theorem 6.2.13? Meron tayong ratio of PDFs given the two samples x and y. We have the ratio of the PDFs. And this ratio of PDFs is independent of the parameter theta if and only if. Meron ganun. So we have a t of x is equal to t of the sample x is equal to t of the sample y. Okay? So kung gusto niyo yung i-verify, it's already 3. Pwedeng ganito. Suppose we have 2 sample points, and x, y, be 2 sample points. Gusto ko sanang tapusin kasi now, we have the PDFs, the ratio of the PDFs, the parameter. So ano yung ating joint? Yung joint natin,
Ultra mega 20. What? I want. Let me score. What is this?
this is raised to n. Kasi joint man yan. Bold kasi ito. Yan, bold. May sabay. Then we have here 1 over theta e to the negative x sub I over theta. Then this is raised to n. Then we have the product of the indicator functions 0 to positive infinity over 1 over theta e to the negative y sub I over theta raised to n. We have the product of the indicator functions y sub I, x sub I, 0 to infinity. Okay, so simplifying this, we have e to the negative summation of x sub I over theta. Okay. Then we have here e to the negative summation of y sub I over theta. Then we have here the product of the indicator function x sub I, 0 to positive infinity. And then we have the product yan indicator function of y sub I, 0 to positive infinity. Okay, so this ratio is independent of our parameter theta if and only if. Ano nga yung sabi natin doon? If we have x sub I is equal to y sub I, or if and only if, all the more, we have the summation of x sub I is equal to the summation of y sub I. That is, okay, the t of the sample is equal to the sample x is equal to the t of the sample y. And so, yung t of the random sample, we're having this, the summation, take note. We have here the summation of the x sub I I from 1 up to n is minimal. Napakita natin na ang T of x sufficient. Napakita natin ang T of x complete. Napakita natin ang T of x minimal. Ngayon, alam natin na ang G of x ancillary. So hence, by Basu's theorem, complete, sufficient, minimal. So by Basu's theorem, T of x and G of x are independent. That's according to Basu's theorem. And then since we're wanting to compute the expected value of G of x. So ito ngayon. Itong x sub n exponential random variable. So ano yung mean ng exponential random variable? Theta. Okay, so that's correct for the first equality. Ano yung x sub n? Dito sa second equality natin. Itong x sub n natin, it could be expressed as the summation of x sub I times x sub n over the summation of x sub I. Okay? So this would be equal to T of the, and then this one, x sub n. No? Tingnan nyo yung g of x natin dito. Diba? X sub n and the summation of the summation of x sub I. Okay, so this is actually the g of x. So ito g of x. Okay, so satisfy yan. And then since we know that t of x and g of x are independent, totoo yan. And then the expectation of t of x. Itong part na to. It is equal to the expectation of t of x. We have the summation of the x sub I. And then we have IID, the summation of the expectation of the x sub I. And we know the mean of that is equal to theta. Because we have n theta. So ito yung results. Therefore, since we are wanting the expectation or we're going to compute the expected value of g of x, so the answer is equal to n to the negative 1. Okay, so lastly, ito yung noted natin dito. It should be noted that minimality of the sufficient statistic was not used in the proof of Basu's theorem. Indeed, the theorem is true with its word omitted because the fundamental property of complete statistic is that it is minimal. Pag may pakita mo na talaga, according to this note, if you can show that your statistic is complete, automatically that is also minimal. But it's not ang converse is not or the converse is not necessarily true. Kapag minimal siya, kahit sufficient pa siya, it would not imply that it's complete. So if a minimal sufficient statistic exists, then any complete statistic is also a minimal sufficient statistic. Pag complete nga siya, it's actually minimal at the same time sufficient. That's according to our definition, to our theorem. Kasi yung theorem 6.2.10 nag-show siya na sufficient statistics siya. At yun pa rin yung halos yung form natin ng ating exponential form ng ating exponential family. So it would say, but based on our the number of components of our parameter as well as the number of components in our statistic, then we could conclude that's a complete statistic. Okay, so any questions or clarifications? This ends for the first principle of data reduction based on sufficiency. So next meeting, I'm going to discuss data reduction based on likelihood function. Any questions or clarifications before we go? Guys?
Wala na, sir.
Okay, so I'm going to stop now the recording. Okay.